Welcome to Introduction to Building Codes, Bangladesh National Building Code 2020, referred to as BNBC 2020, Part 8 Building Services, Chapter 1 Electrical and Electronic Engineering Services for Buildings, Part 2 Electrical Presentation. Our course description. This presentation is designed to familiarize and assist code officials in locating, describing, and applying the applicable code requirements for electrical and electronic engineering services for buildings. Additionally, this course will provide insight on the requirements for designing circuits, lighting, and power distribution as well in our residential and commercial buildings. Our course overview. Internationally, code officials recognize the need for a modern, up-to-date electrical code that addresses the design and installation of electrical and electronic systems through requirements emphasizing performance. This presentation will cover key topics of the following areas. We will look at key areas, key topics, and requirements of scope, terminology, and definitions, distribution wiring in a building, electrical wiring in the interior of buildings, methods of point wiring and circuit wiring as it applies to branch circuits, subfeeds, and feeders. Last, conduits, channels, cables, and conductors will be discussed in this presentation. Seminar goal. The goal of this training is for you to learn and apply key code requirements contained in Chapter 1 titled Electrical and Electronic Engineering Services for Buildings to enhance your performance while inspecting these systems. This training will also provide participants with specific code requirements with examples related to design, installation, and inspection of electrical and electronic systems to further enhance your knowledge. Our course objectives. Upon completion, participants will be better able to locate general topics in Chapter 1 regarding electrical and electronic engineering services for buildings, locate applicable codes and standards for specific situations, apply code requirements to real-world situations, explain the intent behind a given code requirement, and last, use good judgment to identify certain systems and related components as compliant or non-compliant. Chapter 1, Section 1.1, Introduction. Within Section 1.1.1 titled Scope, the provisions of the code presented in this chapter cover the electrical and electronic engineering services for buildings to ensure that the related installation work becomes perfect and safe for persons residing in and around the building. The term safe means safe for the person and safe for the properties. Provisions of the specifications are set minimum standards for electrical and electronic engineering installations, such as various occupancy categories of buildings as described in Part 3 of this code, including annexes and premises. All the systems and equipment intended for supply of normal and standby power to all these places are covered by the provisions of this code. An electrical and electronic code cannot be effective without adequate provisions for its administration and enforcement. When we look at the scope requirement here, It is for the safe design and installation to keep people safe in our buildings from the hazards of electrical and electronic installations. There is plenty of information and requirements to guide the designer, the installer, and the code official with key requirements to have these safe systems built for the end user. Section 1.1.1 Scope continued. There are several hazards associated with electrical systems, including but not limited to shock and burns from contact and building fires from faulty wiring. A properly designed system with a code-compliant installation that is ultimately reviewed, inspected, and approved by properly trained code officials is vital in ensuring electrical systems are safe for people and buildings. The official charged with the administration and enforcement of electrical regulations has a great responsibility to do so. This responsibility drives his or her authority. We need to be understanding of the hazards involved with electrical installation. We need to have qualified people that review, inspect, and approve the electrical systems to avoid such hazards. Additionally, the provisions of this code for various electrical and electronic engineering systems and/or installations for the buildings include, but are not limited to, the following. Lighting and illumination. Lighting and illumination indicated in item A is necessary such that we can function within the building under proper lighting or illumination levels for working, living, eating, cooking, sanitation purposes. Item B, fans, cooling, and heating. These are environmental conditions within the building to keep us comfortable as we live and work in our buildings around Bangladesh. Item C, normal and standby power supplies. Certain occupancies will have standby power supplies as to fortify the necessary need for electrical power within certain buildings. Item D, supply system and feeder for lifts, escalator, moving walk, including protection. Item E gives us cable television distribution. Item F, electronic access control. The scope is also continued in item G regarding burglar alarm, CCTV monitoring, security systems. Item H, electrical cables, conductors, and equipment. Item I, switches, sockets, and other accessories. Item J, cables and conductors in a building that connect the supply of electricity. Item K, electrical protection system. And last, item L, earthing system of an electrical installation. Continuing from the list, item M, lightning protection of a building and its electrical installation. Additionally, we have fire alarm requirements, as the scope indicates, within many buildings that are required to be provided with a fire alarm. Finally, item O, multimedia communications, data communications, and telecommunications. In order to effectively administer the code, a code official must clearly understand to what extent the code applies. As the code official applies a given code provision, the intent is to make sure that the application fits the scope of the code. That is the language that is so necessary in the scope part of the code. The scope, while not entirely complete, does provide a level of clarity as to the work and activities that fall under the provisions of this code. The provisions of this code in this chapter do not cover installations in ship, watercraft, railway, rolling stock, aircraft or automotive vehicles, and recreational vehicles. Continuing with the scope requirements, electrical wiring, cabling, form a major part of the previously mentioned installation works. Electrical wiring and cable must be reasonably safe to person and property. Installations, alterations, extension of electrical wiring and cable systems conforming to the provisions of this code shall be deemed to be reasonably safe to persons and property. If designed and installed in compliance with the applicable portion of this code, an electrical wiring and cabling system is considered safe for people and property. In other words, building, and by administration and guidance of this code, the installation is reasonably safe for the people that occupy our buildings. The code establishes the minimum thresholds for electrical systems to operate safely. Section 1.1.2, Designing an Electrical and Electronic Engineering Installations in Buildings and Related Structures. The provisions of the code presented in this section are not meant to provide adequate information to design electrical and electronic engineering installations and systems in buildings and related structures. These should not be taken to be adequate or complete for the efficient design work of installations. Such design work, the required features, detailed technical specifications, schedule of items, etc., should be obtained through the services of an engineer adequately qualified in this area. Applications of energy-efficient appliances should be kept in mind while preparing electrical design of a building or related installations. The code clarifies here that the code is not meant to be taken or utilized as a design manual to perform complete electrical system designs. It is very clear here. This type of work should be reserved for a qualified engineer, which will use other design references, equations, standards, etc., to complete the electrical design of the proposed building or system within the building as to function properly and safely. Section 1.1.3, Terminology and Definitions. This section provides an alphabetical list of the terms used in and applicable in this chapter of the code. In case of any conflict or contradiction between a definition given in this section and that in Part 1, the meaning provided in this section shall govern for interpretation of the provisions of this chapter. A code provision could be misinterpreted if the definition of a term as used in the context of the code is not understood. The following slides will provide key definitions that will assist the code user to properly understand certain terminology related to this chapter. Codes by their very nature are technical documents. As such, literally every word, term, and punctuation mark can add to or change the meaning of the intended result. This chapter contains several terms that are important to understanding the provisions of this code. Definitions are found both in this chapter and throughout the code. Let's take a look at some key terminology relating to electrical and electronic engineering installations. The term MDB, Main Distribution Panel. This is the distribution box where the main incoming cable enters and terminates from the main service feed connection of a large building. The FDBs get fed from the MDB. FDB is the floor distribution board, located in each of the floors of a multi-storied building. The DBs get fed from the FDB. DB is a distribution board. This may be the box where the main incoming cable enters and terminates from the main service feed connection. The SDBs get fed from a DB. An SDB is a sub-distribution board located in the same floor of a building and is connected to the DB. The BDBs get fed from the SDB. A BDB is a branch distribution board located in the same floor of a building and connected to one of the SDBs in the same floor. As you can see, the language here is abbreviated. Once the qualified code official, engineer, and installer understand this terminology, we can speak the same language. When we see the abbreviations within the code, we know what the terminology means, and we can still go back to this particular section of the code to find out what these certain letters mean if we do not sense the meaning deeper in the code. So we can always go back to terminology and definitions to qualify what these initials mean. The term circuit breaker is a device designed to open and close a circuit by non-automatic means and to open the circuit automatically on a predetermined overcurrent without injury to itself when properly applied within its rating. The circuit breakers are designed to open the circuit on an ampere rating that would exceed the conductor rating in most cases. Therefore, this is a protection method that we have to have in place for feeder circuits, branch circuits, and subfeed circuits as well. The term earth is the conductive mass of the earth, whose electric potential at any point is conventionally taken as 0. Earth lead wire, the final conductor by which the connection to the earth electrode is made. We take earth and use this as a reference. The earth lead wire is embedded into the earth and by means of a conductor is connected to the electrical system for voltage stabilization and transient voltage regulation as well. Earth continuity conductor, abbreviated as ECC. This is the conductor including any clamp connecting to the earthing lead or to each other. those parts of an electrical installation which are required to be earthed. It may be in whole or in part the metal conduit or the metal sheath or armor of cables, or the special continuity conductor of a cable or flexible cord incorporating such a conductor. ECCs of appropriate size must run from a MDB, that is a main distribution board, to its DBs or distribution boards, from a DB to its corresponding SDBs, from a SDB to the switchboards under this SDB, from an SDB to the BDBs, if there are any, from a BDB to the switchboards under this BDB, from an SDB or a BDB to the sockets under this SDB or BDB. As an example, we have a sub-distribution board and we are deriving a subfeed to feed a branch distribution board. All of the conductors are within a cable or pipe. As seen here, the earth continuity conductor is run along with these conductors to the branch distribution board. A note for the code user: in section 1.3.3.2, titled Sockets, Outlets, and Plugs, there is a requirement, and it indicates for 13 amp and 15 amp, 20 amp sockets, the earth continuity conductor shall not be smaller than 1.5 square millimeters, PVC insulated annealed copper. The color of the earth continuity conductor cable insulation shall be yellow plus a green bicolor. Note that the ECC is to be PVC insulated. A bare insulated wire would not be compliant with this section. As we could see the picture, we have a PVC insulated conductor, and the outside color of the insulation is yellow with a green bicolor. The term live, electrically charged so as to have a potential difference from that of earth, also known as alive. We use the term live to indicate the conductor that has a potential difference from that particular conductor when measured to that of earth. Insulation is defined as suitable non-conducting material enclosing, surrounding, or supporting a conductor. Usually PVC, polymer, specially treated rubber are certain types of insulation that we find on our conductors in the electrical industry. LT, LV, and HT, HV is defined as LT or LV in this document indicates 230 volt single phase and 400 volt three phase. HT or HV in this document indicates 11 kV line to line three phase system. We use this definition to indicate our lower voltages and higher voltage systems as well. As an example, below we have a diagram indicating a 230 volt single phase system. This would be indicated as a LV type system or an LT-LV system. And as we can see, we have the voltage limited at 230 volt single phase. The single phase is denoted by the color of the conductors as well that we will cover in a later part of the code here. The live conductor is colored brown, the neutral is colored blue, and our earth continuity conductor is covered with a yellow and green bicolor identification. Chapter 1, Section 1.3.4, titled Distribution Wiring in a Building. Loads are separated into known and unknown loads. General illumination is a known load, whether derived from detailed lighting layout or developed from watts per square meter calculation. Similarly, fans are also known loads. Besides these two types, there may be some other known loads or unknown loads. Number, rating, and layout of outlets for general illumination, fan, and other known loads should be accurately distributed among a number of branch circuits. These branch circuits should then be carefully loaded with due regard to voltage drop, operating voltage, and possible increase in lighting levels in the future. On the other hand, the sockets are unknown loads. Socket loads will be determined from projections based on the utility of the building and type of applications. The sockets that were mentioned here may be for appliances, certain equipment, or just general purpose power sockets. Every installation shall be divided into small circuits, of course, following the rules given in this document, to avoid danger in case of a fault, and to facilitate safe operation, inspection, maintenance, and testing. For the establishment of the circuits, appropriate type of wiring is needed, and appropriate terminations, connections, junctions of these circuits are needed. At the time of appropriate types of protection against faults, we must be given at different levels. These are to be achieved through installation of appropriate distribution wiring in the building. As indicated, we need to look at the terminations. We need to understand how the terminations are installed, the specification, the connections, any kind of junction of circuits to facilitate the distribution of power from different subboards, branch distribution boards, to the final location of the device. Section 1.3.4.2, Distribution Board. A distribution board is the junction point of the incoming line and the outgoing lines for the distribution of electricity throughout the building. The incoming as well as the outgoing lines must have circuit breaker protection or fuse protection. The junctions and terminations of the incoming and outgoing cables are made through copper bars containing bolts and nuts for cable lugs known as bus bars. A distribution board may be named as MDB or FDB or DB or SDB or BDB. As you recall, from our definitions, MDB stands for Main Distribution Board. And recalling the definition, this is the distribution box where the main incoming cable enters and terminates from the main service feed connection of a large building. The FDBs get fed from the MDP. Remembering that FDB stands for Floor Distribution Board. These are located in each of the floors of a multi-storied building. The DBs get fed from the FDBs. Usually more than one FDB are needed. Recalling DB stands for Distribution Board, this may be the box where the main incoming cable enters and terminates from the main service feed connection. The SDBs get fed from the distribution boards. Item D in section 1.3.4.2 indicates SDB is used to represent sub-distribution board. This board is located in the same floor as a building and connected to the DB. Usually more than one SDB are needed. Then the DBDs get fed from the SDB. Item E, BDB stands for branch circuit board, located in the same floor of a building and connected to the SDB. Usually more than one BDB are needed. Last, F, EDB, EFDF, ESDB, EBDB, sections of the distribution board, the floor distribution board, which is FDB, the SDB, and DBD receiving feed from the emergency bus bar, which in turn is getting fed from standby generator through changeover switch. These may be separate DBs placed by the corresponding normal supply DBs. Each of these distribution boards must have bus bars for line, neutral, and earthing for a single-phase box. A three-phase distribution board must have bus bars for line 1, line 2, and line 3, neutral, and earthing. These boxes shall be made with sheet steel of not less than 18 SWG thickness and must be appropriately finished to match the wall paint. As an example, we have a power distribution system indicated in the diagram. From the left lower side, we see that the main service feed enters the main distribution board on the ground level floor. From that point, out of the top of the main distribution board, we run feeders to feed floor distribution boards on upper level floors of a multi-storied building. As you can see here, we have a floor distribution board on floor number 2, a floor distribution board on floor number 3, and a floor distribution board for floor number 4. Each one of these floor distribution boards feeds other panels and ultimately to the suites on that floor. When we look at the main distribution board again on the ground floor, off to the right side we have a feed that feeds power to the sub-distribution board. The sub-distribution board distributes feeders to branch distribution boards that are located on the same floor level, as seen in this diagram. Section 1.3.4.3, titled Circuit Wiring. Item A gives us a requirement for separate branch circuits for separate control. Separate branch circuits shall be provided for different parts of a building area which need to be separately controlled. A branch circuit should be independently working and should not be affected due to the failure of another branch circuit. The number of final circuits, also termed as subcircuits or circuits, required and the points supplied by any final circuit shall comply with the following items. Item 1, the requirement of overcurrent protection, the requirement for isolation and switching, and the selection of cables and conductors. All final circuits shall be wired using loop wiring system. No joint box shall be used. And we need a sufficient number of 18 SWG sheet metal made pull boxes. We must have these given on the walls near the ceiling. If brick walls are not available, pull boxes must be given in the ceilings. Final circuit, by definition, as referenced in this section, means the following: an outgoing circuit connected to one way of a distribution board or a fuse board and intended to supply electrical energy to one or more points, to current using appliances without the intervention of a further distribution fuse board other than a one-way board. It includes all branches and extensions derived from that particular way in the distribution board or fuse board. This section sets out the requirements for separate branch circuits for separate control. Section 1.3.4.3 continued. Item B, for domestic and office buildings. 5-amp light fan circuits must be used for all domestic and residential buildings. 5-amp light fan circuits are also to be used for office and commercial buildings. The corresponding circuit wire in the BDB, SDB, and DB then shall be not less than 1.5 square millimeters. This particular section sets forth the maximum ampere rating of a light fan circuit, as well as giving the minimum wire size of 1.5 square millimeters for these circuits that serve lights and fans in domestic and residential buildings. Item C, for office and commercial buildings having large open floors. Under unavoidable circumstances, in case of difficulties in forming 5-amp light fan circuits for office and commercial buildings having large open floor areas, 10-amp light fan circuits may be used. The corresponding circuit wire in the BDB, SDB, and DB then shall be not less than 2.5 square millimeters. However, use of a 5-amp light fan circuit or circuits is still emphasized. Item C gives you the option, if you have difficulties in forming a 5-amp circuit, gives you the allowance to use a 10-amp circuit for light and fan circuits, only in office and commercial buildings having large floor areas. As an example, we will look at a lighting circuit using a ceiling rose. By definition, ceiling rose is defined as a ceiling rose is used for terminating the point wiring for a light or a fan in the ceiling. It has brass terminals in which incoming cables are terminated using brass screws on the terminals, and the outgoing flexible cables get connected through the screw connections. The ceiling roses are indicated up in the ceiling. This provides a point of termination, or looping if you will, for the circuit that supplies the lighting. Power is supplied to the ceiling rose, and then it is dropped down to the light switches. As we can see the example of a ceiling rose off to the right side, we have our loop conductors that enter into the middle of the ceiling rose. To the left side are our neutral conductors, and to the right side is the line conductors. This is where we make the transition to feed the switches down below, indicated as light switches. We would feed a line conductor down to the switch, a live wire, and then on the load side of the switch come back up to the light fixture itself with a switched live wire, such that when the switch is in the closed position, the light will illuminate. When the switch is in the open position or the off position, the light will not illuminate. Thus, the circuit will be open. All of the connections are made in the ceiling rose accordingly. Another example for domestic and office buildings. 5 amp light circuits must be used for all domestic and residential buildings. Keeping in mind this 5 amp limitation along with the minimum wire size, we have an example of a branch distribution board, 230 volt single phase system. We have a circuit breaker in the branch distribution board feeding a branch circuit. There is 3 wires located within a cable or a pipe. We have our live wire that's indicated with the color brown, the neutral wire indicated with the color blue, and our earth continuity conductor, our ECC, which is a yellow and green marking on the insulation. We take that cable, that branch circuit, and feed it into the first ceiling rose. From this first ceiling rose, we take that and loop it to the next ceiling rose. From that point, we now distribute the switch power down to the light switches. As can be seen here, the power from the BDB is wired into each ceiling rose, in and out, then looped on to the next ceiling rose. The switch cable and the flex to the lighting fitting are connected at the ceiling rose accordingly. Our next example is for office and commercial buildings having large open floor areas. Our code section or reference gave us the option to use a 10 amp light fan circuit when we have difficulties in forming a 5 amp light fan circuit. The corresponding circuit wire in the BDB, SDB, or DB shall not be less than 2.5 square millimeters. In our diagram below, we have a branch distribution board. This is a 230 single phase system. We have a 10 amp breaker that is protecting our conductors. We have a live, a neutral, and a earth continuity conductor, EEC, in a pipe or a cable. This is a 10 amp circuit. The circuit wires indicated here are 2.5 square millimeter, and it feeds ceiling roses again where we have the looping wiring method to supply power and switching for the switches that operate the lights within our commercial buildings. Continuing on with section 1.3.4.3 titled Circuit Wiring, item H. Branch circuits must have spare capacity to permit at least 20% increase in load. This is required for each branch circuit running between a distribution board, a sub-distribution board, and a sub-distribution board and a branch distribution board. They must have spare capacity to permit at least 20% increase in load before reaching the level of maximum continuous load current permitted for that circuit. So right here we've got a level of safety in that we need to design in a 20% increase in load accordingly. Item I, one spare circuit must be allowed in the distribution board for each 5 circuits in use. Additional space for a circuit breaker along with the provision for connecting a pair of outgoing cables shall be kept. This particular section allows for future expansion or future capacity of an additional circuit when you have 5 existing circuits. Item J, each final circuit shall be connected to a separate way in a distribution board. Where an installation comprises more than one final circuit, each final circuit shall be connected to a separate way in a distribution board. The wiring of each final circuit shall be electrically separate from that of every other final circuit, so as to prevent unwanted energization of a final circuit. Continuing on with section 1.3.4.3, circuit wiring. Item K. Size of cables in a branch circuit shall be at least one size larger than that needed for the computed load current. Size of cables to be used in a branch circuit shall be at least one size larger than that computed from the loading if the distance from the overcurrent protective device to the first outlet is over 15 meters. As an example in the diagram, we have a branch distribution board. In that branch distribution board, we have a 5 amp circuit breaker that protects the conductors of a branch circuit. The conductors are seen exiting the branch distribution board. We have a live conductor, a neutral conductor, and our earth continuity conductor. The total distance measured in this case is over 15 meters. So for a general lighting circuit in a domestic or residential type occupancy, we were given the minimum wire size we could use as 1.5 square millimeters. We must increase this wire size up 1, which would be 2.5 square millimeters due to the distance being over 15 meters. This, ladies and gentlemen, compensates for voltage drop. We need more conductor area due to the resistance that is being afforded to this long distance. For a lower voltage drop, we use a larger wire. A note to the code user, Appendix B, Table 8.B.1 gives us some useful information regarding common wire sizes. This particular table we can utilize to understand the conductor cross-sectional area for common wire sizes. As seen in the table, we have a 1.5 millimeters squared all the way to a 50 millimeters squared wire accordingly. All of the wiring in between is common wiring size. Now off to the left of the table here, conduit diameter. We're given typical conduit diameters and how many wires can be inserted into the conduit based upon the cross-sectional area. Continuing on with circuit wiring, section 1.3.4.3, item M, length of a lighting circuit. The length of a lighting circuit shall be limited to a maximum of 30 meters. Unless the load on the circuit is so small that the voltage drop between the overcurrent protective device and any outlet is below 1%. This section is giving us a requirement for voltage drop. We want to be kept below 1% regarding the voltage drop. Consider the diagram below. The limitation of our lighting circuit is 30 meters. This circuit is from where the overcurrent protection device supplies power to the light and switching. We must measure the conductor length all the way through as indicated in the diagram. If this conductor length is longer, we must consider voltage drop. In some cases, we may have to increase the wire size accordingly to compensate for voltage drop. Again, we're given a limitation as to what the maximum voltage drop is, and it needs to be below 1%. Item N, use of common neutral for more than one circuit is prohibited. Each circuit must have its own neutral cable. And again, the use of common neutral cable for more than one circuit is not permitted. Circuit wiring continued. Section 1.3.4.3, item O. Following the appropriate new color codes of cables. During wiring, correct color codes of the insulation of cables must be used. Previously, for a single-phase, red color insulation was used for the live wire, and the black color insulation for the neutral, and green plus yellow bicolor insulation was used for the ECC. Previously, for a three-phase circuit, red color was used for the live L1, yellow color for the live L2, blue color for the live L3 cable, and the black color for the neutral, and green plus yellow bicolor for the ECC. This color code of cable shall not now be replaced by the current IEC Cable Color Code Standards. Table 8.1.21 and Figure 8.1.1. The current IEC color code is recommended to be followed in Bangladesh. We will look at the tables and color coding in the following slides. Table 8.1.21, titled New Introduced Color Codes of Cables Following IEC Standards. Our first column indicates the item. Protective earth, PE, neutral, N, single-phase line, L, three-phase, L1, three-phase, L2, and three-phase, L3. Pre-1977 IEE, the protective earth color was green, the neutral was black, and single-phase line was red. The three-phase were given to us as three-phase L2 was yellow and three-phase L3 was blue. This again is pre-1977 IEE standard. When you run into existing systems that have been wired according to that standard, these are the color codes that were referenced at the time of installation. The next column is pre-2004 IEE. The protective earth conductor is colored green, yellow bicolor. The neutral, black, single-phase line, red. Three-phase L2 is yellow, and three-phase L3 is blue. And as can be seen here, the only difference between pre-1977 and pre-2004 was the introduction of the green-yellow bicolor for the protective earth conductor. Our current standard, our current IEC in Bangladesh, has the color codes that must be followed for all new work. For the protective earth conductor, green, yellow bicolor. The neutral is now blue in color. Single phase L1 is brown, as well as our three-phase L2 is black and three-phase L3 conductor is gray. These are the new colors complying with IEC standards that must be followed. The above-mentioned color coding must be indicated in the design drawing. This should also be mentioned in the specification as well. Figure 8.1.1, titled Existing and Harmonized Color Code by IEC Recommended for Use in Bangladesh. On the left side, we see the existing color codes, where L1 was red, L2 was yellow, L3 was blue, and our neutral existing was black. Harmonized now, current colors administered by IEC standards in Bangladesh must be L1 brown color, L2 black color, L3 gray color, and the neutral now is blue color. And again, the above mentioned color coding must be indicated in the design drawing. And this should also be mentioned in the specification. Once the installers have the approved electrical drawings and specifications, they will see the new colors that are indicated in these construction documents and properly install the correct color coding on the conductors and system accordingly. This way, it's easy for anybody to service, maintain, or even add on to the systems and understand the color coding with respect to the different phases and neutrals of our systems. As an example, we have an existing three-phase feed into a sub-distribution board. As the feeder comes in from the bottom into the breaker, which is our overcurrent protection device, notice the colors of the phase conductors. On L1, it's a red color. L2 is yellow, and L3 is blue. This is an existing panel, existing wiring. So when we go back to figure 8.1.1, we can use the code to properly identify these particular colors based on the existing standards. As well as we can see that we also have green wires used as the ground or earthing wires accordingly. Section 1.3.4.3 Circuit Wiring Continued. Item P, balancing of circuits in three-phase SDBs, DBs, FDBs, and MDBs. In a three-phase distribution system, special care must be taken during wiring to obtain balancing of loads amongst the three phases. In a three-phase SDB, DB, FDB, MDB, connections of the circuits to the bus bars must be made in such a way so that the load current remains balanced amongst the three lines during low load as well as full load. After completing the installation, balancing should be checked by clamp meter current measurement of each phase. The above-mentioned current balancing must be indicated in the SDB if three-phase. The DB, the FDB, and MDB circuit diagram of design drawing. This should also be mentioned in the specification. Now, this section tells us the requirement that we must balance the system. We have three live wires carrying current. The current carried from the utilization equipment, the power outlets, the lighting, must be balanced in each phase. An example given here is connections of the circuits to the bus bars. After completing the installation, balancing should be checked by a clamp meter current measurement of each phase. The previous code section indicated that we need to balance the circuits, the conductors, especially in three-phase systems. I have in front of us the feed from a main distribution board. We have a breaker that controls or verifies overcurrent protection as a limit. If that was a 100 amp breaker, we have balanced loads coming back of 84 amperes in each phase. L1, the brown phase, 84 amperes. The black phase, L2, 84 amperes. And the gray phase, L3, 84 amperes. This comes from my SDB load that is under load, and we've measured it accordingly at the high period of utilization. We also need to measure this at the low period of utilization as well, just to make sure the system is still balanced. Section 1.3.5, titled Electrical Layout and Installation Drawings. An electrical layout drawing shall be prepared after proper locations of all outlets for lamps, fans, fixed and transportable appliances, motors, etc. have been selected. This is the beginning of the electrical distribution design work. This job must be done with due importance prior to starting the construction and installation work. Strong emphasis is given on this work in this document. The language used here indicates that we must have an electrical layout drawing prepared. This must take place prior to construction and installation of the work, due to the fact that the engineer must analyze, must estimate, must understand all of the loads within the proposed building to design the electrical system safely, and convey that to the authority and installers providing the work to be done in our buildings. Section 1.3.5.1, locating positions of the points on the plan of the building. At the beginning, the light points, fan points, socket points, switchboards, BDBs, SDBs, FDBs, DBs, and MDBs shall be located on each plan based on convention, suitability, application, and safety viewpoint. Conduit layout and conduit cable layout shall then also be shown on the drawing as well. The electrical engineer must provide specific information on the electrical layout drawings and effectively communicate the proposed installation. Section 1.3.5.2, light and fan circuits must not be mixed with the socket circuits. In designing the wiring layout, power, socket, and heating socket subcircuits shall be kept separate and distinct from lighting and fan subcircuits. All wiring shall be done on the distribution system with main and branch distribution boards placed at convenient positions, considering both physical aspects and electrical load centers. All types of wiring, whether concealed or surface, shall be as near the ceiling as possible. In all types of wiring, due consideration shall be given to neatness and good appearance. This particular section drives the fact that there is no mixture or intermingling of light and fan circuits with power sockets and heating socket subcircuits. We must keep these separate and distinct. Section 1.3.5.3, balancing of circuits in three-phase installation shall be arranged in the drawing and also must be done during physical connection. The electrical engineer must provide specific information on the electrical layout drawings and effectively communicate the proposed installation to those that are installing the electrical system. Good installation of wiring must be as near to the ceiling as possible and installed neatly with good appearance. Balancing the loads. This is the ampere or current that flows through the individual conductors in three-phase circuits must be provided in the design drawings and followed through with the installation of conductors on the job site. An example of circuit routing and identification of power outlets is given below. We have a commercial office building, and as indicated, we have receptacles, we have identification of our main distribution board, our lighting boards, which is a lighting panel, is indicated on the right-hand side. The circuits are also identified that supply the outlets. As can be seen in the left-hand side, LP-1 is a load panel. It is circuit 21 indicated for that final wiring back to the panel that supplies our outlets. Preparation of detailed circuit diagrams are given as a requirement in section 1.3.5.6. Circuit diagrams of each of the light and fan circuits must first be prepared based on the selection whether it is 5 ampere or 10 ampere circuit. This is the maximum ratings of light and fan circuits. The cable size of each of the circuit size of the ECC must be shown in the drawing as well. The circuit diagrams of the BDBs, SDBs, DBs, FDBs, and MDBs, etc., are then to be prepared and presented in the form of single-line drawings indicating the cable sizes of each interconnection and the sizes of the ECCs. The distribution of BDBs, SDBs, DBs, FDBs, MDBs, etc. are to be shown in a distribution drawing indicating the cable sizes of each interconnection and the sizes of ECCs. Within section 1.3.5.7, it indicates, as titled, Preparation of Electrical Distribution and Wiring Design Drawing by an Experienced Engineer. Electrical distribution and wiring design drawing of building must be prepared by an eligible engineer as mentioned in Table 2.3.4, Chapter 3, Part 2. As an example, we have a circuit routing and identification lighting plan for a commercial office area. We have a general plan view indicating the circuiting, the number of light fixtures, as well as some notes and the legend for the light fixtures. We have double fluorescent lamp fixtures indicated as lamp fixture A. We also have night light circuit, and the fixtures are so indicated NL on the drawing. If we look at the lighting layout accordingly, we have the wires and the routing indicated to each particular light fixture, as well as the locations in the rooms, which are the offices, and the central corridor. When we look over to the legend, as indicated, we have a double fluorescent lamp on ceiling indicated as fixture A, and the night light fixture with the note, all night light, exit light, and emergency lights to be connected ahead of all local lighting switches. This is due to, if there is a power failure, we would have battery backup in this particular fixture to provide a level of illumination for a predetermined number of minutes to allow people to egress out of the building safely. Indicated as well with this particular design is the note that all lighting circuits are protected with a 5 amp circuit breaker, and the wiring is 1.5 millimeters squared copper wire. Lighting circuit shall be limited to a maximum of 30 meters. Section 1.3.6.1 gives us a requirement for surface wiring or exposed wiring. Wiring run over the surface of walls and ceilings, whether contained in conduits or not, is termed as surface wiring or exposed wiring. This particular section gives us the requirements for proper wiring with respect to this type of installation. Single core PVC insulated copper through PVC channels or through PVC conduits or through GI pipes of approved quality may be used for surface wiring. Surface wiring using twin core, flat PVC, insulated copper on wood battens used to be used long back. This is almost discontinued and discouraged nowadays. This section specifies materials for surface and exposed conduits. In the pictures below, we see PVC conduits and GI pipes, when used for surface wiring, shall be clamped with saddles at a spacing not exceeding 600 millimeters to the wall or ceiling using plastic rowel plugs with countersunk galvanized screws. This will give secure support for these piping materials. Another section regarding electrical wiring in the interior of buildings is section 1.3.6.2, concealed wiring. The wires in this type of wiring shall be placed inside GI conduits or PVC conduits that are buried in roofs and in brick concrete walls. The conduits in the wall shall be run horizontally or vertically and not at an angle. Very specific here in the introduction of concealed wiring section here. Horizontally or vertically, they may not be run at any angles whatsoever. Conduits in concrete slabs shall be placed at the center of thickness and supported during casting by mortar blocks or chairs made of steel bars or any other approved means. All conduits shall be continuous through their lengths. This particular area mandates that the conduits be placed in the center thickness of the concrete, and they must be supported to that elevation with steel bars, chairs, mortar blocks, or any other approved means. Appropriate planning must be made in which there shall be adequate spare capacity in the conduits placed in roof slabs so that unforeseen situation during execution of the installation can be taken care of. Conduits will run through the roof and then bend downward for going up to the outlets, DBs, switchboards, and sockets. In a column structure, building having no permanent walls, switchboards and socket boards, pull boxes shall be placed in columns and must be done during the casting of the columns. So this particular section indicates that we must put in the piping in the columns during the casting of the columns for our equipment such as switchboards, socket boards, and pull boxes accordingly. So we must plan for the installation as well. Wiring inside suspended ceilings or false ceilings. Section 1.3.6.3. When we have wiring inside these spaces that we call false ceilings, it shall be surface wiring through conduits or through PVC channels mentioned under the heading of surface wiring methods. Therefore, we must go back to the previous section regarding surface wiring methods for this particular area within our buildings. Cable shall not be placed loosely in haphazardly on the suspended ceilings. Placing naked cables inside the suspended ceiling is not permitted. Cable joints with PVC tape wrapping is not allowed for connection of a fitting from the ceiling rose or from a junction box inside the gap space. PVC insulated copper through PVC channels or through PVC conduits or through GI pipes of approved quality may be used for surface wiring inside suspended ceilings. As seen here, the picture indicates a suspended ceiling, which is dropped down from the structural ceiling and provides a space for wiring. It also provides a space for plumbing and mechanical ductwork and piping as well. We can use the surface wiring methods to wire in lighting from above this particular space. Mounting height of light and fan switchboards. In section 1.3.6.5 provides the requirement that light and fan switchboards shall be placed 1,220 millimeters above the floor level in residential buildings. In other words, the clearance between the floor and the bottom of the switchboard shall be 1,220 millimeters. This above-mentioned height shall be 1,300 millimeters above the floor in the office buildings, commercial buildings, and industrial buildings. However, the minimum height shall not be below 1,220 millimeters. In the diagrams below, on the left, we have a floor level in a residential building. We measure from the finished floor level to the bottom of the switchboard, and we must be at least 1,220 millimeters above the finished floor. The floor level in commercial and industrial buildings is shown on the right-hand side. We can see that the elevation measured from the finished floor level in these buildings to the bottom of the switchboard shall be 1,300 millimeters above the floor level for these particular buildings. Section 1.3.7, titled Methods of Point Wiring and Circuit Wiring, gives us the requirements accordingly. Section 1.3.7.1 in particular, titled Methods of Point Wiring. Wiring between a light fan point and its corresponding switchboard is termed as point wiring. The load of such a point is not in excess of 100 watts in general, and in special cases, this may be up to 200 watts. Wiring for a light fan point shall be made using one of the following two methods. Item 1, surface wiring method, or item 2, the concealed wiring method. For wiring of a point, one brown and one blue PVC insulated copper cable shall run between a point and its switchboard. Cable joints, inside conduits, or within channels are forbidden because these joints will be concealed. It is not allowed according to our code. The current carrying capacity for such a circuit shall not be more than 5 amperes for a residential or commercial, business, mercantile included. The minimum size of a cable for such wiring shall be 1.5 millimeters squared. Common neutral shall not be used under any circumstances. Section 1.3.7.2 provides us with methods of circuit wiring. Wiring between a switchboard and a BDB, SDB, DB will be called circuit wiring. Circuit wiring shall be done with a live cable, a neutral cable, and an ECC cable for a single-phase circuit. Sometimes this circuit is also referred to as sub-circuit. This particular initial section gives us for a single-phase system, meaning the circuit between the switchboard and distribution panels, as indicated here, must be done with a live cable, a neutral cable, and an ECC cable. This circuit, again, is called a sub-circuit. An ECC must be provided within each circuit, or with and running with each circuit. The ECC at the switchboard end shall be terminated in the earth terminal of the metal part of the switchboard using a brass screw, bolt, and a nut. The BDB, SDB, and DB end of the ECC shall be terminated in the earthing bus bar of the BDB, SDB, and DB. The ECC in this case shall be the PVC insulated copper cable of appropriate size, but with yellow plus green bicolor insulation. For each circuit, the live cable must be drawn using brown color insulated PVC cable, and the neutral cable shall be drawn using blue color insulated PVC cable. A common neutral shall not be used under any circumstances. An example is given here in the diagram below of a sub-circuit including a live cable, a neutral cable, and a ECC cable for a 230 volt single phase feed circuit. We look at the main distribution board, MDB. This is where the service conductors come into the building, into the main distribution board. From this board, we have a sub-circuit consisting of a live conductor, a neutral conductor, and an earth continuity conductor, ECC. This is our sub-circuit. This may be run in a conduit, galvanized GI pipe, to the sub-distribution board. This is correctly indicated as a sub-circuit. Methods of circuit wiring is continued. The minimum sizes of cable for various uses shall be as follows. Item A, for 5 amp circuit protection by a 5 amp circuit breaker or fuse shall not be below 1.5 millimeters squared. Item B, for a 10 amp circuit protected by a 10 amp circuit breaker or fuse shall not be below 2.5 millimeters squared. Item C, for a 15 amp circuit protected by a 15 amp circuit breaker or fuse shall not be below 4 millimeters squared. Item D, for a 20 amp circuit protected by a 20 amp circuit breaker or fuse shall not be below 6 millimeters squared. The above-mentioned sizes must be increased for long cables, as mentioned elsewhere in this document. That means when we have long lengths of run, we have more resistance and therefore a large voltage drop. In general, The minimum size cable for a particular circuit shall depend on the rating of the fuse or circuit breaker used for the protection of that circuit. A voltage drop check is to be made for each length of the circuit to ensure that the voltage drop at the farthest end of the load from the main distribution point does not exceed 2.5%. Sockets shall get direct connection from the BDB, SDB through breaker or fuse protection. Depending on the assessed requirements, sockets may be grouped, looped at the socket end. Such grouping shall not exceed 3 numbers of sockets in one circuit. This particular section gives us the ampere rating of the circuit, the ampere rating of the circuit breaker or fuse, and gives us the minimum sizes of cable for various uses as well. And also mentions the voltage drop to take into consideration due to the length of conductors when we install them in buildings. Section 1.3.8, titled Feeder Wiring between a Sub-Distribution Board and a Branch Distribution Board, a Distribution Board and a Sub-Distribution Board, a Floor Distribution Board to a Distribution Board, a Main Distribution Board to a Floor Distribution Board, etc. Wiring between these distribution boards and a main distribution board needs special attention, and the rules are similar to circuit wiring. Earth continuity conductor, or ECC, must be present for each of the feed connections. The ECC in this case also shall be PVC insulated copper cable of appropriate size, but with green plus yellow bicolor insulation. At both ends, the ECC must be terminated at the earthing bus bar. This particular wire, the earth continuity conductor, is the conductor that carries ground fault current back to its source and allows the overcurrent protection device to open the circuit on ground faults. Appropriate cable lugs, cable sockets, must be used for terminating the L1, L2, L3 neutral and ECC connections on the bus bar of both the boards. The sizes of the cables must be chosen to match with the rating of the circuit breaker, fuse ratings, as mentioned above. Circuit breakers or fuses must be provided at the outgoing and incoming sides of each of the bus bars of each BDB, SDB, DB, FDB boxes. An example of wiring between a main distribution board, a sub-distribution board, and branch distribution boards is indicated below. The ECC, or the earth continuity conductor, is run with live and neutral conductors and conduits, with ends of the ECC terminated at the earthing bus bar. We start on the left-hand side of this 230-volt single-phase system. The main service feed is introduced into the main distribution board, along with the earth continuity conductor, the neutral, and the live being derived as a sub-circuit from the main distribution board. It is routed from the main distribution board to the sub-distribution board. As can be seen here, the earth continuity conductor is fastened at the metal bar inside the subdistribution board. From the subdistribution board, we have 3 feeder circuits, 2 branch distribution boards. The first feeder feeds branch distribution board number 1, and noting by inspection, the earth continuity conductor, ECC, is also bonded to the inside of the branch distribution board. We have a feeder from sub-distribution board that feeds branch distribution board number 2. And the same thing happens with the earth continuity conductor, ECC. It is bonded to the metal bar within the branch distribution board number 2. Finally, the last feeder that originates from our sub-distribution board feeds branch distribution board number 3. And the earth continuity conductor is again connected to the metal bus bar in the branch distribution board number 3. This particular diagram shows a routing of the sub-circuit and feeder circuits to the associated sub-distribution board and branch distribution boards with the continuity of the earth continuity conductor. This conductor carries any type of ground fault current back to its source to allow the overcurrent protection devices such as breakers and fuses to safely open the circuit on ground faults. Section 1.3.9, titled Conduits, Channels, Cables, Conductors, and Related Accessories. A section that references conduits and conduit fittings is given to us in section 1.3.9.1. It indicates that cables of an electrical distribution installation are drawn through electrical conduits. For the installation of conduits, various types of fittings are needed. For the 2 types of commonly used conduits, PVC and metal, fittings should be as under A, PVC conduits. Item number 1. PVC conduits and conduit fittings shall be of heavy wall, water grade type. All bends shall be large radius bends formed by heat or mechanical bending machine. The cross-section of the conduit shall remain circular at the bend, and the internal diameter shall not be reduced due to bending. PVC pipe fittings shall be sealed with PVC solvent cement or adhesive for PVC of approved quality. Item number 2, conduits installed in floors, if installed, shall have a slope of at least 1 in 1,000 towards the floor-mounted pull box or cable duct. This is for any condensation that could occur within the conduit piping system. Item number 3, conduits placed concealed inside roof or in wall must have 20 SWG GI pull wires placed during laying of the pipes for pulling the cables later. Item number 4, water grade PVC conduits must be used for both concealed and surface wiring. Water grade PVC conduits of different diameters shall be used as per necessity. This makes it important that we use water grade PVC conduits for both concealed and surface wiring. Item number 5, appropriate high grade bends and circular boxes must be used with PVC pipes. Item 6, 18 SWG metal sheet made and synthetic enamel paint coated quality boxes of matching sizes shall be used as pull boxes and junction boxes. Appropriate pull box covers of ebonite or perspex sheet shall be fitted with GI machine screw and washer. This particular item indicates the sustainability and durability that needs to be afforded from good quality boxes such as pull boxes and junction boxes as well. Item number 7. The PVC conduits placed concealed inside roof or in wall must have 20 SWG GI pull wires placed during laying of the pipes for pulling the cables later. Continuing with section 1.3.9.1 for conduits and conduit fittings, item C, PVC flexible pipes and conduits. PVC flexible conduits shall be used with surface wiring only, and only in places where PVC bends cannot be used. Except special circumstances, flexible PVC conduits shall not be used. Item D gives us requirements for metal and steel conduits. Galvanized iron, GI, conduits shall be made using at least 16 SWG sheet. The conduits shall have seamless joint along the length and must be suitable for making bends. No projections are allowed inside the conduits. Metal conduits must be threaded for end-to-end joints using sockets. In case of necessity, threads will be cut at the end of the short pieces. Sharp edges at ends must be properly treated so that cable injury does not take place during cable pulling. In other words, we must file down the inside edges due to the burr that is on the conduit of metal conduits. When we cut the conduits, we must make that smooth such that the cable does not get damaged while pulling the wire through the conduit that we call galvanized iron conduit. Item E of the same section for conduits and conduit fittings gives us requirements for pull boxes. A pull box is used for long runs of conductors where we must have a location to pull from. Item number 1, pull boxes, joint boxes, must be placed close to the ceiling where conduits from the ceiling are going downward toward a switch box or are going toward a socket box or are going toward a BDB, SDB, DB, or an FDB. Item number 2, pull boxes are extremely essential for pulling the cables without injuring the cables and thus should not be avoided under any circumstances. These are also essential for future maintenance and extension work. Item number 3, pull boxes, joint boxes must be placed in the ceiling of office, factory building where conduits are running over a long distance between two walls or terminal points, and where fixed walls are not available, and also where heavy beams are used. In case of big cross-section beams, pull boxes, joint boxes shall be placed close to the beams. Item number 4, pull boxes, joint boxes must be made with 18 SWG galvanized iron sheet or with 18 SWG MS sheet, but coated with 2 coats of gray synthetic enamel paint. Again, we want to make sure that the durability of these pull boxes stays intact for many, many years. Item number 5. Covers of pull boxes should be ebonite or perspex sheet of not less than 1/8 inch thickness. Item F. Metal boxes for switchboards. Section 1.3.9.2 Cables and Conductors. For application in building wiring, PVC insulated stranded cables shall be used for live and neutral wires for single phase, and 3 lines L1, L2, L3, and 1 neutral for 3 phase. For ECC, which is the earth continuity conductor, also PVC insulated stranded cables shall be used. As a result, use of bare copper conductors or any other type of conductors is non-existent and non-permitted. As an example, we have our 230 volt single phase system. As we can see from the main distribution board to the sub-distribution board, we have our subfeed circuit. All PVC insulated stranded cables within GI pipes can be seen between the main distribution board and the sub-distribution board for our single phase system. Once we derive feeders from the sub-distribution board, we have separate feeders again to our branch distribution boards. Branch distribution board number 1, number 2, and number 3. All of the associated feeders contain a live wire, a neutral wire, and our earth continuity conductor. And as in this design example, they are all PVC insulated stranded cables within galvanized iron pipes. An example diagram is indicated below for a 3-phase system. We have a 400 volt 3-phase system. Our main service feed comes into the left of the main distribution board. From the main distribution board to the sub-distribution board, we have a subfeed circuit consisting of 3-phase conductors, a neutral conductor, and our earth continuity conductor, the ECC. As you will see here, L1, L2, L3, the neutral wire, and the ECC are all PVC insulated stranded cables within galvanized iron pipe. This feeds the sub-distribution board. Of special note, you will see that L1 is colored brown, L2 is colored black, L3 is colored gray, with our neutral being indicated as the color blue, and the earth continuity conductor, ECC, again is green with yellow, as indicated in the IEC new standard for color coding of this system, which is the 400 volt 3-phase system. Cables and conductors continued in section 1.3.9.2. Item A, cables. Conductors of a PVC insulated cable, thin or thick, shall be copper. Cable containing aluminum conductors may be used for thick cable of size more than 35 millimeters squared. But copper is always preferred. This is an important statement. Copper is a better conductor compared to aluminum. However, aluminum is preferred for thicker cables more than 35 millimeters squared. Cables for power and lighting circuits shall be of adequate size to carry the designed circuit load without exceeding the permissible thermal limits for the insulation. The voltage drop shall also be within the specified limit of 2.5% from a distribution point up to their farthest end of the load point. Recommended sizes in millimeters squared of copper conductors are as follows. As we can see, the range between 1 and 1,000 millimeters squared is our conductor areas. The standard copper conductor sizes of cables which should be used for electrical installations, distribution in buildings are given above. Conductor of sizes other than sizes listed above are not recommended. As you can see, it ranges from 1 to 1.5, 2.5, and goes all the way up to 1,000 millimeters squared. For final circuit, sub-circuit, and for light fan point wiring, the cable nominal cross-section of the cable shall not be less than 1.5 millimeters squared for copper conductors. We must keep this in mind based upon the circuit that we are designing. Our code indicates certain minimum conductor sizes that we have to design and install at a minimum. So the code user is noted here to verify these minimum conductor sizes. Cables and conductors continued. Item B, phase and neutral cable shall be of the same size. In the wiring of sub-circuit, circuit, and all other circuits inside a building, the phase cable and the neutral cable shall be of the same size. As indicated in the pictures below, the phase cable and the neutral cable need to be of the same size. If we have a 2.5 millimeters squared cable, a phase conductor, the neutral wire must be the same size as indicated. 2.5 millimeters squared neutral for that particular cable phase size. In the adjacent to the right 50 millimeters squared phase conductor size, I will have to size the neutral at 50 millimeters squared as well. This is designed to carry the full current on the neutral back to its source. Section 1.3.12.2, titled Size of the Enclosure of a BDB, SDB, DB, FDB, MDB. Particularly, the section 1.3.12.2 indicates requirements for size of this enclosure for these distribution boards. Table 8.1.22 provides a guidance of sizes of enclosures for SDB containing miniature circuit breakers or fuses. However, the size will depend on the number and size of the circuit breaker or fuses, the number of outgoing cables and their sizes, the size of the bus bars, and the type of insulators used in the bus bars. Table 8.1.22 is titled Recommended Enclosure Size for MCBs and Fuses. We can see in the dimensions given in millimeters, there is a height, width, and depth according to the enclosure. The very last column of the table indicates the number of MCBs or fuses permitted to be in this enclosure. As an example, if we have the Height of the enclosure at 610 millimeters. The width is 390 millimeters and the depth is 120 millimeters. We can have up to 36 MCBs or fuses within the enclosure. Inspection of the installation is required and given to us here in section 1.3.42.3, item 5. On completion of wiring, a general inspection shall be carried out by competent personnel in order to verify that the provisions of this code and that of the Electricity Act of Bangladesh have been complied with. A certificate may be issued on satisfactory completion of the work in a format as shown in Appendix C. Items to be inspected are detailed in the following sections. We will now take a look at Appendix C and the certificate required by this section. In Appendix C, we have the completion certificate form regarding electrical works. It indicates that this is a certification that the installation detailed below has been installed by the person responsible for installing the work, and indicates several lines that need to be filled out. The electrical installation at a particular location is required. The voltage and system of supply information is required. The particulars of works indicated in item A, internal electrical installation, requires the number, total load, type or system of wiring for lighting points, fan points, socket points of differing sockets, such as 2-pin 5-amp sockets, 3-pin 13-amp flat pin sockets, and 3-pin 15-amp round pin sockets. Item B, the applicant must provide the description, horsepower or kilowatt, and type of starting of various motors. Item C, if the work involves installations of overhead line and or underground cable, then information such as the type and description of the overhead line is required, the total length and number of spans is required, and number of street lights and its description. The form is continued on the following slide. Continuing the completion certificate form, item 2, total length and size of underground cable, number of joints, end joint, T-joint, straight through joint, requires a numerical value for the number of these joints in every case. Item D, earthing, description of earthing electrode, number of earthing electrodes, type and short description of brass earthing clamp, number of brass bolt nuts provided in the brass earthing clamp for the termination of earth lead cables, the size of each of the main earth lead cables, and number of main earth lead cables provided. Test results is the next category. Item A, insulation resistance values. A1, insulation resistance of the whole system of conductors to earth in mega ohms. Next, insulation resistance between the phase conductor and neutral. This is item number 2. Item number 3 is for polyphase systems. The insulation resistance between the phase conductors in case of polyphase supply. As you will see here, The old existing color code is indicated with respect to the colors of phases. This is the old existing IEE standard. A note to the code user with respect to the completion form here, any new installations would need to be changed to the new color code indicated in the IEC standard. Next is item B, polarity test. Polarity of non-linked single pole branch circuits, and C, earth continuity test. A continuation will follow on the next slide. Continuing the completion certificate form, maximum resistance between any point in the earth continuity conductor, including metal conduits and main earthing lead in ohms. Item D, earth electrode resistance. Resistance of each earth electrode must be indicated in ohms in each case, depending how many electrodes are installed and being tested. Item E, lightning protective system. Resistance of the whole of the lightning protection system to earth before any bonding is effected with the earth electrode and metal in on the structure in ohms. Last, the signature of the supervisor is required, name and address below, and the signature of contractor is required, name and address below. This would complete the certificate form for the electrical works. This is the end of the presentation. Thank you for your participation.